Supercharged Science Cast, Episode 13, Lasers. Hello and welcome to the Supercharged Science Cast, our weekly science and math classes for kids, parents, and teachers, where we discover how to do real hands-on science and learn how to use math as a tool in everyday life, and how to use math and science together. Now, my name is Aurora. I'm a mechanical engineer. I'm a university instructor. I'm an astronomer. I started flying airplanes when I was 16. I worked for NASA before I even finished high school, and I did high school at the same time I did college, and total overachiever. And I'm also super passionate about both math and science and sharing it with you. Now, today we're going to be doing lasers, but before we get started, if you have a question and you'd like to send me an email, you can do so through my website, which is at www.superchargedsciencecast.com. Okay, let's get started. Have you ever wondered why you can't just take a flashlight and shine it through something optical like a lens and really narrow, get the beam narrow and concentrated, just like a laser beam is, and turn that into a laser? See, I get that question a lot from students, and it has to do, the reason why is it has to do with the way the light was generated in the first place. See, a laser beam looks like a really narrow, concentrated beam, but it's more than that, and that's what we're going to talk about today. So the first thing I'm going to do is I'm going to give you an overview of what a laser is, and then I'm going to get more into the physics part of it for those of you who already are familiar with the atom and what's inside the atom, and talk a little bit about that as well. And then I'm going to show you one of my very favorite of all time laser experiments that you can do just with a couple of cheap, inexpensive things you've got around the house, and also a laser, of course. So, okay, so that's what we're going to do. So, laser. What is a laser anyway? Could you tell me? If I asked you and I was standing right in front of you like I am now, what would you say? What is a laser? Okay, so the difference between a laser and a flashlight is the way that the light is generated. Let me explain. Can you imagine a bunch of kids in a room and you've removed all the furniture? Everything breakable is gone, furniture's gone, wall hangings are gone, everything. And so you basically just have four walls, a ceiling, and a floor. And you've lined those four-wall ceiling and a floor with mattresses, and the really bouncy and the cushy ones, the ones that it looks like a bounce house inside. And the only thing that you give those kids to eat all day long are sugar cookies. Now you tell me, what's going to happen in that room before too long? Yeah, they're going to go bing, 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 bouncing all over the place, right? So that's very much what happens inside of a laser, only instead of kids, we have particles, little light particles called photons, and instead of mattresses, we have mirrors, and instead of sugar cookies for energy, we have electricity in the form of batteries or just plugging it into the wall socket. So in order to get the light out of the laser, though, in order to get the kids out of the room, we have a little cat flap, and it just opens, and if a kid happens to be bouncing in that direction at that right time, the cat flap opens, the kid goes out, cat flap closes. So only one kid goes at a time. And so when it opens, the kid's coming, and out they go, and it comes back down. And they're bouncing, here they go, and it's pretty soon, this is opening, closing, and kids are flying out, and the kids are all in a straight line. Okay, so that's the overall big picture of what a laser is and also how it's different from a light bulb. When you turn on a light bulb, where does the light go? It goes everywhere, right? It'd be like taking off the roof or even taking off the walls and saying, okay, kids, go for it. And all the kids go flying all over the place. So, which sounds fun, right? So a light bulb is different in that the light goes everywhere. And it also is different in a couple of different ways. I'm going to have to talk to you a little bit more about what a laser is, kind of the physics behind it, so you can really get a taste for what the differences are. Okay, so let me break this down for you. So the word laser, what does that mean? It actually wasn't a real word before it was developed, in that laser actually stands for something. Every letter, L-A-S-E-R, stands for a word. Do you know what it is? Yeah, laser is an acronym for light amplification by stimulated emission of radiation. Ooh, that's a mouthful, isn't it? Let me break that down step by step. Okay, so lasers are optical light that's amplified. Amplified, what does that mean? That means you start with one particle of light called a photon, and you end up with more than one when you're done. That's amplification. Okay, stimulated emission, that's a little bit more tricky to talk to you about. So let me break this down. So stimulated emission means the atom that you're working with. Remember, atoms are like little dots that make up everything in the whole universe. Kind of the way that Lego bricks kind of make up up different things. You can build different things with different Legos. And there's different kinds of Legos. And you can build like ships and bridges and houses and giraffes and robots and all kinds of things, right? Well, atoms are the same way. And different atoms, you put them together in different ways, you get different things, like a penguin or a violin or a bridge or a person. So okay, so atoms, depending on the atom you're working at, atoms can be at different levels of energy. Normally they hang out in a lower energy level. But if they get excited by, say, if you pump extra energy into it, the atom's going to get excited, and it's going to, one of the electrons is going to jump up or one or more of the electrons is going to jump up to a higher state, a higher energy level. And when a photon comes along, a little light particle comes by and interacts with that atom, if that photon has exactly the same energy as the jump the electron made, two things will happen. And the first thing is the electron will jump down to the lower state. And the second thing is it will also emit a photon identical to the original one. So what do I mean by identical? Meaning that it's going to be the same color, and also it's going to be in sync. And have you ever noticed that you don't see like rainbow lasers? The way you, for example, if you shine a laser through a prism, you can't split it into different colors the way you can with regular light. Like light from a flashlight, if you put it through a prism, you can unmix it into its other colors, right? Well, that doesn't work with a laser because lasers are what we call monochromatic. They're all the same wavelength, and that happens because of the way the light was generated in the first place, by that electron jumping down and emitting a photon that was exactly the same as the one that interacted with the atom in the first place. So the other thing is all those atoms are in step, they're in phase, and we call that light coherent light, and that's what a laser really is. Now the light from a light bulb or a flashlight or even the fluorescent lights over your head, those are not coherent, incoherent, and that means that the light's going all over the place and it's all out of phase. And so coherent light, so lasers are monochromatic, one color, and they're coherent. If you think about like an army, okay, you can imagine a bunch of soldiers when they're marching across the plain, boom, 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 boom. They're all, the step that the first guy takes is exactly in sync with the step the last guy takes, right? So everything's in sync, and that's what laser light is like. And did you notice like in the army, they're all wearing the same outfit? Like there isn't one guy in a t-shirt and one guy in shorts over there and one guy a bandana on his head. No, they all wear the same thing. They're all monochromatic in that way, okay? So laser light is the same thing. It's all the same color. It's all the same wavelength, which is why on lasers you can read the little tag. It'll say 632 nanometers. That's the wavelength the laser is emitting. You'd never see that on a light bulb because light bulbs are emitting all kinds of wavelengths, right? Okay, so the end result is that you have photons that are all the same color, monochromatic, and in sync with each other. And so, and again, it has to do with the way the light was generated in the first place. You say, okay, I got it. Well, there's one more step. What's the last letter of the word laser? It's R, right? What does R stand for again? It stands for radiation. Now, most people totally freak out when they hear the word radiation. They think, oh, something really bad. Well, they're right sometimes, but sometimes they're not. And radiation has a bad connotation to it, and not all radiation is bad. In this case, it just means the light in the laser. For example, if I had a flashlight and I shined it on you right now, I would be radiating you, but no harm would come to you, right? So light is electromagnetic radiation. Some radiation is bad, and you definitely want to pay attention to that kind of radiation, but we're not talking about that high energy, high level radiation that can damage your cells. We are talking about just the light that actually started the process of stimulated emission. That was when that electron jumped between energy levels and generated that photon. And the light amplification means that you started with one photon and you ended up with two, or more than two, because you can do this process over and over and over again. Okay, so let me show you now a really cool experiment that I really want you to try. Now, if you don't have the materials for it, don't worry. I want you to watch it anyway so you know exactly what to do once you get your materials. And I want to take you step by step on actually how to measure tiny little objects with a laser. I mean, you might have heard about this before, and you might have been confused like I was, like, well, wait, how can you shine light on something and measure it? That sounds weird. So I'm going to show you step by step how you do it, because actually what you're going to do is you're going to measure the angle that the light bends around it. You're going to measure how much it diffracts, and then use that to back out with a simple math equation, surprise, surprise, on how actually that tiny little image, how big the small little thing is, or how small that small little thing is. Anyway, so I'm going to walk you through it step by step. So again, if you don't have your materials, don't worry. Just sit back, relax, and watch me do it in front of you. And then when you do get your materials, you know exactly what to do. Okay, are you ready? Here we go.
So do you have thick hair or thin hair? Now I'm not talking about how many hairs you have on your head, but the actual width of a single strand of hair. We're going to use a laser and the ideas behind diffraction in order to measure the width of your hair, and actually it'll come out in micrometers. So let me show you what you need to do in order to do this really cool experiment. You're going to need a calculator and a pencil. I'm going to use a marker so it shows up better. And you're going to need a laser, and this can be a regular keychain laser, or it can be a Heaney laser, whatever you happen to have, and a clothespin or a rubber band, and a ruler and some tape, and you also need a sheet of paper. Now this is going to be pretty hard to see, but I've got a strand of hair here, and I'm going to put it so it's straight across the hole that my laser beam comes out of. Now, if your hair is like mine, it's wiggling all over the place. So what you do is you put a piece of tape on one end, and then you stretch it across, and then you tape down the other side. Just like that. Now, once you've got your hair across the open end of the laser, what you want to do now is make it so the laser stays on. Okay, so when I hold the laser and I shine it, it shakes a little bit. So what I want to do is have it shine without me actually holding it. So you can place the button in the jaws of a clothespin and it'll stay on, just like that. Now if you don't happen to have a clothespin, or if your laser is larger so it doesn't fit, you can simply wrap a rubber band around and around and around so that it stays on just like that. Now, you don't want to do this with a green laser, because if you keep those on for too long, they will burn out, and also green lasers are not to be used indoors, which is where we're doing our experiment. Okay, so the next thing you want to do is you want to set this up so this part of your laser where the beam is coming out is 1 meter away from a wall. Okay, so use your ruler to measure. A meter, by the way, is 3.28 feet. And so measure out that distance and set your laser so it's that far away. Okay, and then you want to let your laser go. You don't want to touch it during the experiment because then it's real wiggly. Okay, we're going to be doing some careful measurements with it. Okay, so on your wall, that's where you're going to take your sheet of paper, and wherever that laser beam, that dot, winds up, that's where you want to tape your sheet of paper, because we're going to be making some marks on the paper around the laser beam, and we don't want to mark up your wall. Okay, so go ahead and tape this to the wall. Then I'll show you what to measure. Now this may be hard to see because the center dot here is so bright, but what we're looking for is we're looking for the first two dark lines around the bright dot. And so you put a mark around the first two dark lines that are around that bright dot. Okay, so I've put my 2 marks around the dark lines, and then I'm going to measure with my ruler. Okay, and I get about 8 centimeters. Now to do the calculation to figure out what the width of your hair is, first thing you need to do is figure out what the frequency is of your laser, what wavelength the laser is operating at. Now every laser is going to be a little different. Mine is 650 nm. Now that nm stands for nanometers. So this funny symbol here means wavelength equals 650 nanometers. Now if I were to write that out longhand, I would have a 0 point, and then I'd have 6 zeros, and then a 650 meters. Okay, so simply moving the decimal point 9 places, n is 10 to the 9th, I'm sorry, 10 to the minus 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's how we get between those two numbers. Okay, and you remember the distance we were from the wall was 1 meter. Okay, and again, if you were measuring in feet, make sure that you were 3.28 feet from the wall. Okay, or for our calculation, we're actually going to use meters. We're going to use the SI system. Okay, and then what we're going to do is the distance between the two dark lines for me is 8 centimeters. But I have to convert that to meters also, because when we do our calculation, everything has to be in the same units. Okay, so we have meters here for our wavelength, meters for our distance. The small d is the distance between those two dark lines. And 8 centimeters, you divide that by 100 to get 0.08 meters. Okay, just like that. All right, so how do we do the calculation? So the hair width is going to be equal to the laser wavelength times the distance to the wall divided by the distance between the dark lines times a half. Okay? And so when we do this calculation, I'm going to get 0.000000650 times 1 divided by 0.08 times a half. And so when you get your calculator out and you do your calculations, my hair width based on these numbers, HW, is going to be 0.0000162 meters. Okay, that's pretty small, and it doesn't mean a whole lot, so let's change it to micrometers. And to do that, you're going to multiply by 1,000,000. And so you're going to move the decimal place over 6 points. 1, 2, 3, 4, 5, 6, so I get 16.2 micrometers. So my hair is about, if I were to convert that to inches, 0.00063 inches. Now you give it a try.
So wasn't that cool? So that experiment works because it scatters the laser light on the hair, and the scattering creates a diffraction pattern. You remember that? It looked like a line of lightness. So a laser line got, the dot of a laser got sandwiched out to a long line, and it looked like somebody came in with an eraser and erased part of the laser light. That's the diffraction pattern. And if you know the distance between a couple of those dark areas, as well as the distance you are from the wall to where you're actually shining the laser, the distance from the laser to the wall, you can use those simple math equations, and actually I think I narrowed it down just to one math equation for you, and just plug in the numbers that you need, and you can get the width of the hair. Now, something I want you to try is, I want you, next time you do this experiment, is I want you to actually rotate the hair and watch the diffraction pattern. Now, if you watch carefully, you're going to find something happens to curly hair that doesn't happen to straight hair. And I wonder, what do you think might happen to gray hair? Or white hair? All right, so you can actually find out what the cross section of the hair looks like by rotating it. Isn't that interesting? So how do you think you could modify this experiment to measure other small things like bee pollen or cells, like blood cells? Something to think about, huh? I've actually had a number of students take this science experiment and turn it into a science fair project and actually win awards from it. So that's why I want to share it with you, because it's so cool, and I think you guys should try it, or you personally should try it and take it and run with it and see how far you can go. Okay, it's time for me to be wrapping things up for today. There is a downloadable student worksheet that goes with this topic for you teachers out there. Just print it out, use it as part of your lesson plan, or if you're a parent of homeschool kids, go ahead and print it out and share it with them and add it to your science curriculum. Now, if you're a parent looking for enrichment for your child, suppose they're just thirsty for more science, or maybe your school system doesn't provide enough science in the way you think it should, go ahead and just add this to their current curriculum. It's an awesome, awesome project to have in their science experience of science adventures. So go ahead and use that as well. Now, you'll find the downloadable student worksheet right underneath this video on my website, which is at www.superchargedsciencecast.com. Just enter in your email address and I will send you that student worksheet that goes with the class today. It includes data tables and the equations in them that you need. So, and also where to find the equations if you want to go further. Okay, so the next time we get together, we're going to do some math, and after that, we're going to do some science. And I want to thank you so much for the privilege of being your coach, teacher, and guide along this science journey. I hope you enjoyed learning something new and something that you got out of it. Maybe you didn't know but when you first started, as much as I enjoy sharing what I know with you. Now, if you'd like to replay this class, you'd like access to the free downloads that I mentioned, just go to www.superchargedsciencecast.com, and I will see you in the lab.